Hello everyone, today on our remote sensing lecture series we are going to focus about the sensors, platforms and the orbital characteristics. Previous few lectures we talk about what basic definitions about remote sensing and the process of remote sensing, then the elements of remote sensing in lecture 1, then we came to electromagnetic spectra in lecture 2, and lecture 3 we focus about the characteristics of a remote sensing image. Then next lecture we talked about what are the types of resolutions of remote sensing image. Today we are going to talk about some additional stuff, especially focusing on platforms and scanners and sensors of which are used in remote sensing. Before that we should have an idea what is a satellite, because usually when it comes to spaceborne platform we focus about satellites, and we also need to pay attention towards the satellite systems launch for till this day and have a rough look at them, and we need to understand what is a satellite. So in space, remote sensing is sometimes conducted from space shuttle or more commonly from satellites. So basically satellites are objects which revolve around another object. So you may wonder, is Earth a satellite? Of course. So according to Earth, when we consider Earth, we can see Moon is another satellite which is a natural satellite. So there are two types of satellites, natural and man-made. So Moon is a natural satellite. So wherever the man-made satellites include these platforms we're going to discuss, which were used for our applications in remote sensing, such as telemetry purposes, communications, navigations, etc. So the coverage of these satellites mainly depend on the orbit of the satellite. So there are different classifications of orbits according to our purpose. So basically there are three types of orbits. One is low Earth orbit, other one is medium Earth orbit, third one is high Earth orbit. Or you can classify orbits as this: one is geosynchronized, and other one is polar orbiting or sun synchronized, and another one is geostationary. So polar orbiting is, there are the main thing when we talk about polar orbiting is we had to decide the repetitivity of the satellite according to the orbit. So we can't decide satellite's repetitivity by when designing the satellite. That's one of the disadvantages of polar orbit. Then geostationary, it can be decided when we design the satellite. So here we focus about how this classified in according to this the altitude. So low Earth orbit altitude is less than 2000 kilometers, and between 2000 to 36,000 kilometers it is medium Earth orbit, and from that onwards is going to be high Earth orbit. Then orbits are here when we talk about low Earth orbit. Polar orbiting satellites, polar orbiting or sun synchronized satellites are one of the examples for this LE orbits. So satellite is passed above the Earth poles. That's why we call polar orbiting satellite. And high resolution images are possible and crosses equator at 90 degrees, as you see in this picture. And also the advantages is every time the satellite views the newest segment on Earth's surface because of the satellite's rotation. So you can have a newest segment on Earth's surface with the rotation of the Earth. So first orbit like this, and second orbit like this, third orbit like this. You can see each time there's a newer segment comes and there's a newer view with the rotation of satellite. That's one of the key advantages of pole orbiting satellites. You can always have a fresher look on the surface. And also the angle of inclination of the orbit with respect to Sun throughout the year is same when it comes to synchronized, so or polar orbiting satellite. So these satellites always crosses the equator precisely the same local sun time. And also these are the types of orbits which used most in remote sensing. As you can see, angle of inclination with respect to the sun is always the same, as you see in this graph, throughout the year, and crosses the equator precisely the same local time. So September 23rd here, and June 21st, March 21st, 22nd December for each equal number of days gap, so crosses the equator at the same time. You can see that the equator crosses at the same time with having the same inclination of the orbit respect to sun. Here's another, this is what I meant previously. So inclination is always the same with respect to sun wherever the earth is, so in this plane. Then when it comes to near pole orbit, then here orbital plane is inclined a small angle comparing to the previous one. The inclination angle is much smaller. Then we come to high Earth orbit satellite, or we call it geostationary orbit. Is one of the high Earth orbit satellites. So better to keep these types of orbits in mind as I told you, as geostationary or pole orbiting instead of high Earth orbit, or medium Earth orbit, or low Earth orbit. So it's up to you. You can memorize these things. It's okay to memorize both. So when it comes to geostationary orbits, satellite placed in this orbit stationary with respect to Earth and view the same area of Earth at all times, and at one time it covers 50% of global surface, and orbital period is 24 hours. So for 12 hours it covers 50% of the Earth, and 12 hours later it covers the rest. Advantages of this orbit is useful in meteorological observations and also for commercial and broadcast and communication purposes. So satellites provide a great deal of remote sensing imagery. As I told you earlier, they have several unique characteristics which made these tasks particularly useful for in remote sensing regarding a surface. So simply the orbit is the path of a satellite. So orbits are matched to the capability and objective of the satellite. So then comes to disadvantages of this geostationary orbit. So low resolution, actually, as you see, 1 pixel revert to 2.5 kilometers on the ground, so it's slightly low resolution. Less information is obtained due to low resolution. So when it comes to choice of the orbit, we especially focus about the objective and the capability of the satellite. Otherwise, objective means its mission. So as an example, low Earth orbit was designed according to necessity of high resolution images. So commercial broadcast communication satellites were launched in higher Earth orbits because instead of resolution they focused on receiving and sending signals for large geographical area. So you can see how orbit was chosen according to the purpose. So here you can see sun synchronized orbits, and in green color and red color covering the poles, and also in purple and red they are geostationary geosynchronized orbits. So there are some when it comes to land surveying and cartography users, we use sun to synchronize. So lower orbital satellites, and when it comes to communication and navigation purposes, we come to geosynchronized satellites. As you see in this weather forecasting, we use also geostationary satellites. So geostationary satellites are used in communication, weather purposes, and also geosynchronized satellites are used in navigation purposes. Like that, you can see applications and also the example for each application in this graph. So I'll keep it for a while to have a screenshot or have a better look while pausing this video. Here you see. Then we comes to remote sensing platforms. Before that, I will look a bit about further look about have a discussion about what I've said earlier. So as I said, orbit is the path taken by a celestial body or the satellite moving at a constant speed around another celestial body, in our case the Earth. So it's a man-made body. So when it comes to satellite, it's a man-made body sent to space for experimental or any other purpose which around the Earth. So orbit selection can be done with the terms of altitude and their orientation and rotation related to the Earth. Then there are some other characteristics we need to focus when it comes to satellites. One is altitude, and altitude. Another one is orbital characteristics, and also inclination angle. When it comes to orbital characteristics, altitude is one and inclination angle is another, and also period of the orbit or orbital period, and also repeat cycle. I told you when I discussed about scan line and radiometric temporal resolution. I told you about this repeat cycle. So here you see, when it comes to altitude, it means the distance from the satellite to the mean surface of the level. As an example, orbit at 600 to 800 kilometers or 36,000 kilometers are the altitude respectively of polar orbit satellites or geostationary orbit satellite. So this distance influences to a large extent which area is viewed and at which detail. Then we come to inclination angle of an orbit, which is the angle between the orbit and the equator. So it is called an inclination angle. So it determines, together with field of view, or otherwise FOV, of the sensor which latitude can be observed. Then we comes to period of the orbital period. Otherwise, this is referred to the time taken to a given object make one complete orbit around another object. So polar satellite orbit at 800 kilometers altitude has a period of roughly 90 minutes, and ground speed of 28,000 kilometers per hour is having the period of 8 kilometers per second. Then let's focus about repeat cycle, which I mentioned earlier. Sometimes places that when it comes to repeat cycle, it refers to the time between two identical orbits, two successive identical orbits. If I want to be more clarify, so the revisit time, or the time between two subsequent images of same area, is determined by this repeat cycle, joining the pointing capability of the sensor. So you may wonder what is pointing capability. It is possibility of sensor to look sideways, simply. So when it comes to, as I told you earlier, keep that on mind when don't put additional stuff like LE or ME or OHE or classification. Just keep there are two types of orbits. One is geostationary, another one is near polar synchronized. So when it comes to, I'll have a rough introduction about geostationary orbit, if I may. So this refers to simply orbit which satellite is placed above the equator. It means inclination angle is 0 degrees at a distance of 36,000 kilometers. So at this distance, the period of satellite is equal to the period of Earth. So that's why we call this geostationary. And this result geostationary. So then this result, the satellite is a fixed position relative to Earth. So there are certain disadvantages of this type of satellite. So the great distance from the Earth and lower the resolution needs. The spatial resolution achieved by this type of satellites, as an example, weather satellite. So sufficient for the purpose of weather forecasting, but when it comes to imagery, it is a bit we can't be more satisfied with that. So there are GOES, Meteosat and Intelsat, INSAT are some examples for geostationary satellites, and exactly 284 hours orbital period. And also orbital circle is on the same plane where the equator is. So there are some stuff you need to keep that on mind. And also this satellite doesn't move with respect to the Earth, and also when it comes to applications of geostationary orbital satellites and telecommunication and Earth observation weather forecasting comes to first. and also at once these type of satellites can cover half of the earth, as I told you earlier. In case center of an image is the point where a line from Earth center to satellite intersects with the Earth's surface, and when it comes to it moves towards the edge, or when it moves towards the edges of image, you can see due to low resolution large geometric distortions occur with cause simply the spatial resolution is very poor, and also the high altitude. And when it comes to sun synchronized or near polar orbits, the orbit is chosen. The satellite always passes overhead the same local solar, which is called sun synchronized. This allows a satellite to record images at two fixed times during 24-hour period, so one during the day and one during the night, as you see, and also inclination of 90 degrees with the equator is another characteristic of these types of satellites. And also every pass on around the earth pass over both north and south poles, and also the satellite scans one horizontal line at a time, and also entire globe is covered by one sun synchronized satellite for every 14 days. Earth rotates to east underneath the satellite, which travels north and south, and therefore that's why it can cover the whole earth. So when it comes to this satellite, these are important in geophysical and meteorological side, of course in weather forecasting. Altitudes usually range from 700 to 800 kilometers with period of 98 to 102 minutes, and complication time of a circle per day is 14-16 complete circles for one day. So these satellites revisit the same area of Earth approximately same local time, as I showed to you with the use of graphs, and in this way equal animation of geometry is preserved for images can be done in different dates. So, and also we can see how the seasonal changes occurs when it comes to remote sensing images, and also 60 to 185 kilometers swath width of a strip is provided by these types of satellites. So that's about orbits of the satellite and the characteristics of the satellite, and let's move further. So let me talk about platforms of the satellite. So platform of a satellite is simply where sensor is being held, which is called a platform, or in other words we can say it is a stage to mount the camera or sensor to have information about the target which is being investigated by the sensor or simply the camera. It can be a vehicle or another type of carrier. In remote sensing these are called borne, so space borne, airborne and other stuff. So you can see types of platforms ground-based platforms. There are three types of GB ground-based platforms. One is short range, another one is medium range, and long range systems. Then comes to airborne platforms. Then we come to airborne platforms and also spaceborne platforms. So there are few facts we need to consider when we considering about a platform. One is the flight course, another one is altitude, another one is orbit. So there are three factors we need to focus when considering about platforms of remote sensing. One is altitude, one is orbit, one is flight course. Okay, let's go. So ground-based platforms, usually the mobile hydraulic platforms is one of the examples for this, and also when it comes to 50 meters height, we focus about these type of sensors which can be mobile, can be easily explained by giving an example like a vehicle. So then comes to portable masts, which are unstable in wind conditions, and when it comes to towers, these are not unstable in wind, which has a greater rigidity comparing to a portable mast. And also when it comes to weather surveillance data, which detects and tracks typhoons, cloud masses. These are another type of ground-borne platforms. And it comes to airborne platforms, which acts at the altitude of 24 to 22 to 40 kilometers roughly. These are tools for being, as an example, you can take balloons, which can be defined as a tool to probing the atmosphere. And also these are useful to test instruments development. When test runs, these are used. And also radio sound is another example for these types of airborne platforms, which measures pressure, temperature, and relative humidity of the atmosphere, and also rewinds on which measures velocity of wind, and also temperature, pressure, and relative humidity is another type example for airborne platform. And when it comes to this type of aircraft airborne platforms, there are certain types of advantages when it comes to aircraft. So this aircraft generally used to acquire area photographs for photo interpretation, and also primarily stable to wings. Aircraft are used, wings has to be stable, or occasionally helicopters are used. It's okay. So I used to collect detailed images and facilitate the collection of water over any portion. Center maintain is easy when it comes to aircrafts, and also there's higher spatial resolution, one of the advantages, and analog photography is possible, also digital, and also easily schedule can be changed according to weather. So sensor maintenance is also easy. When it comes to disadvantages, permission to intrude into foreign countries or foreign areas is a bit difficult, and many passes to cover the large area, and also swath is less comparing to satellite, and satellite can far deeper in space can cover larger area, that's why, and high cost per unit area is another disadvantage. When it comes to spaceborne platforms and sensors mounted on spacecrafts and rocket satellites, space shuttles are examples for these, and also they cover large area of course, and repetitive coverage is possible. Then we can focus about these type of sensors. Then we come to sensors after, when it comes to, before that, when it comes to let's have a quick feedback about the three types of platforms. One is ground-borne, space-borne, and airborne. So when it comes to ground-borne, Earth resources are studied, mainly used for collecting ground truth for laboratory simulation studies. So these types of sensors can be placed in a ladder, tall building, or something like that. And comes to airborne platforms, aircraft are generally used to these type of aerial photographs and photo interpretation, and these platforms are primarily stable wing aircraft. Occasionally helicopters can be used. Then we comes to spaceborne platforms. These are not affected by key thing is one, this not affected by Earth atmosphere, and also these platforms freely moving in the orbits around the Earth. Entire Earth or part of Earth can be covered. Therefore, satellite. Then we can discuss about satellites under these spaceborne platforms, and I told you what are the characteristics of satellite and their orbital characteristics. Then we come to the sensors. So it's one of the key things we have to discuss in remote sensing. Before come to sensors, let me have a revision on quick revision on process of remote sensing. When it comes to process of remote sensing, you can also say this see some stages of remote sensing. So these stages directly deals with the sensor. One is when it comes to the energy source, it emits electromagnetic radiation, as an example sun or any other energy source. It emits the electromagnetic radiation. So that's the stage one of this remote sensing. So second stage is that energy transmits from source to the surface while facing atmospheric reactions such as absorption and scattering. We'll have a look at them later. And then intersection of electromagnetic radiation with Earth's surface can be happen through reflection or emission. That's the third stage of this remote sensing. And fourth one is that energy transmission from surface to the remote sensor. That's the fourth part. Next, sensor outputs data. Then that data is being transmitted or processed. So there are 6 stages of remote sensing. One is energy is being emitted, and second one is it's being transmitted from a source to the surface, and third one is it intersects with the Earth's surface, reflection or emission, and fourth one is it's being transmitted back from surface to the sensor, and sensor output data. That's the fifth one. Sixth one is transmission, processing or analyzing part of the data. So sensor can be defined as a device which measures or records electromagnetic energy, or sophisticated device that are frequently used to detect and respond to electrical or orbital optical signals. So Sensor converts the physical parameter into signal which can be measured electrically. So since the intersection between radiation and the object intersect conveys information required on the nature of the object. Abroad, satellite sensors obtain information about features and object on Earth by detecting radiation reflected emitted in different bands of electromagnetic spectrum. So when it comes to sensors, another definition can be defined as the same way. You can memorize if you want. I'm not going to discuss here. There are types of sensors. One is active and one is passive, and they are subdivided to other types later. So active sensors are called which sensors which emits energy and detect reflections simply, or which detect reflect responses from objects which are radiated from artificially generated energy sources, can be simply defined as active sensors. And passive sensors, of course, these are the sensors which detect reflected or emitted electromagnetic radiation from natural sources. So there are two types. Then passive sensors divide into another two types of another two categories. One is non-scanning, another one is scanning. Also active remote sensing also divided into these two categories as well. And non-scanning, when it comes to passive, divided into non-imaging and imaging categories. And there are some examples for non-imaging passive remote sensors and imaging passive remote sensors. These are examples for non-imaging, non-scanning passive remote sensors and imaging non-scanning passive remote sensors. So have a look at this chart and try to wrap up these things into your head. And also, yeah, that's it. So you can see when it comes to active and passive remote sensing, when it comes to non-scanning or framing remote sensing, it means it measures the radiation coming from entire scene at once. It's an example, cameras or our eyes. So you can see examples for these type of sensors. And imaging sensors means from image form an image. This type of imaging sensors form an image by collecting radiation. There are two types for this, and one is scanning sensors. This here scene is sensed by the point by point, and which is equal to the small areas. So there are two types of these type of scanning sensors. One is a long track, another one is a cross track. So when it comes to a long track, scanners, these can be said a push broom. These type of scanners acquire information image by line, or these they use forward motion of the platform to record dimensional image which is perpendicular to flight direction. Instead of scanning mirrors, they have a linear array of detectors, so located at a focal plane of image. And these type of scanners have a lens system which are pushed along the flight track direction as well. So the array scanning system here has no moving optics. It's one of the advantages of these type of things. And sensing element is a linear array of several detectors. These type of detectors are called CCD. Yes, CCD it means I thought I prepared a slide regarding that, but I haven't. So CCD means charge coupled devices, which stands for detectors which called linear array of several detectors. So these are aligned parallel to the ground and perpendicular to the flight direction, as you see in this graph. And also, when it comes to long track scanners, the forward motion of the sensor advances the position of this sensing array over the sea. That's why these called a push broom. So these are designed for multispectral sensing operations which have separate arrays of CCDs. So that's it. And we comes to a cross-track scanners, which is also called push broom. As you see, image is acquired by pixel by pixel, this here line by line, here pixel by pixel. So these are scanned in a series of lines, as you see, and also these lines oriented perpendicular to the direction of motion across the swath, and also each line is being scanned on side of the sensor to the other using rotation mirror. But when it comes to long track, we don't use rotation mirror but array of detectors. Successive scans build a two-dimensional image of Earth's surface, and emitted radiation is being separated into several spectral components which are detected independently, and also UV visible, near IR and thermal radiation are dispersed and to their constituent wavelengths. And internal detectors are there when it comes to this type of scanners. So they are sensitive to specific range of wavelength and detect and measures that energy for each spectral band, and filters are used to restrict the wavelengths. Then also instant field of view of the sensor, as you see in this figure. Then also the altitude of the platforms determines the ground resolution cell, as you see in the figure. The angular field of view, which is mentioned here, is the sweep of the mirror, measures in degrees, used to record scan line and determines the width of swath. And that's it. And also these line scanning sensor systems use single detector per wavelength. That's another key thing you need to memorize. And this the size of image element of Earth's surface is related but not necessarily equal to the IFOV. That not necessarily equal to IFOV is something you need to put that into your mind. Strictly I consider that. And when it comes to non-imaging sensors, these type of sensors don't form an image, that's why we call them non-images, and they are used to record spectral quantity or parameters such as a function of time, example temperature or atmosphere. And when it comes to imaging plan scanning, lens is used to after the scan mirror to do the focus the light on the detector as shown in the figure. The lens is used after the scan mirror to do the focus. And when it comes to object plan scanning, it is referred to, lenses. Here lens is being placed before the scan mirror to focus the light on the detector. So when it comes to imaging and non-imaging platforms, we can see that non-imaging sensors, we can say that both active or passive sensors are divided into selecting and non-selecting type of scanners. Then when it comes to those non-scanning and scanning categories, both divided into imaging and non-imaging. So these imaging sensors are divided into image plane and object plane, that's why we discussed here. So object plane, lens is placed before the scan mirror, and here lens is used after the scan mirror in image plane. So when it comes to passive sensors, passive scanning image plane scanners, we can say TV camera, solid scanner as an example. And also when it comes to active non-scanning image plane sensors, we can say real aperture radar or synthetic aperture radar. And also when it comes to active scanning imaging object plane scanning, we can say as an example passive phased array radar. And also when it comes to passive scanning object plane scanning, microwave radiometer, optical mechanical scanner can be said into the examples. So those are the things we need to discuss about sensors. And when it comes to active and passive sensors, I can say satellite systems can be divided according to this active and passive categories. So as an example, you can say when it comes to active passive satellites, one is advanced very high resolution radiometers and spot also, and also Landsat series, IRS, which is not used today, Iconos, and also Cartosat, GOES, Metrosat, CY, and also Terra EOS, which are the observing satellite series. When it comes to have a rough look on this type of satellites, so when it comes to Metrosat, this is a program sponsored by 17 European weather services, which was started in 1977. This type of this was stationed above the equator at 0 degrees longitude above the Gulf of Guinea, and image this part of globe every 30 minutes. There are 3 wave bands for these Metrosat: visible, water vapor, and also thermal IR Then another passive passive sensors NOAA, which National Oceanic Atmospheric Administration. That's what NOAA stands for. So these have advanced very high resolution radiometer instruments to image planet in 5 bands. One band is from 0.8 to 0.68 to 0.8 micrometers. One is to 0.725 to 1.1 micrometers. 3.5 to 3.93, 10.3 to 11.3, 11.5 to 12.5. Those are the areas of wavelength bands. And also when it comes to GOES satellite system, it stands for Geostationary Observational Environmental Satellites, which was launched in 1974, and GOES Next was launched in 1994. And these types have 5 wave bands from 0.55 to 0.75. One is to 3.8 to 4, 6.5 to 7, 10.2 to 11.2, 11.5 to 12.5 micrometers, which varies from resolution varies from 4 kilometers to 8 kilometers. And also we can't ignore space shuttles. Basically, space shuttles are the manned aircrafts, which manned aircrafts on a mission carrying astronauts, scientists, and instruments. They have shuttle image radar sensors, metric camera sensors, and also large format cameras which use LFC, and also multispectral scanners. And also when it comes to Landsat series, which was launched in 1972 and latest one was launched in 1978, there are 6 Landsat satellites, and 4 and 5 are still operational, but 6 was failed. So these type of Landsat satellites complete orbit every 90 minutes. So near polar sun synchronized satellite system, which revisits 16 days, and altitude is from 438 miles or 705 kilometers. So Landsat 123 carries multi-spectral scanners with 80 meter pixel resolution and records data across 4 wave bands or 3 visible channels and 1 near infrared. And 4 and 5 Landsat satellites are more refined. They have more refined multispectral scanners which used for thermatic mapper on board with band 6 resolution of 30 meters and terminal IR resolution of 120 meters, and 7 wavelength bands and included here. Landsat 7 was launched in 1999, and this additional stuff I just comes to my head, with the resolution of band 6, I guess 30 meters of Landsat 4 and 5, so it must be 60 meters, I think. So that's it about satellite system which are passive. So when it comes to active sensors, also I need to talk about spot satellites. And this spot satellites has an altitude of 832 meters and have a sun synchronized near polar orbit satellite system. So this have a push broom scanner, which surface immediately below the nadir view, or can be directed so that the view surface of the site These type of satellite systems are important because it means two views in the same area and it be collected within short time of comparing to each other, because the system can take two images of the same area with different angles. We can have a 3D image. So then computer can create a digital elevation model which known as DEM for these images. And when it comes to active sensors, we have radar set 1, which launched 1995 by Canada Space Agency SA for crop investigations, coastal soil mapping. These are some primary objectives of this radar set. And also when it comes to active sensors, ERS series is ERS 1 and 1 2, which launched 1991 and 1995 respectively, uses sun synchronization, polar orbit, and also these are used to collect difficult to observe collect the information about the areas which are difficult to observe. And ERS2 comparing to ERS1 has an upgrade of GOME, which referred to Global Ozone Monitoring Experiment instrument. So I mentioned about you when it comes to spot about push broom scanners. Then when it comes to push broom scanners, I would like to look into some advantages and disadvantages of this type of scanners. So when comparing sensor types, there are 6 sensor types roughly. So there are 6 sensor types roughly can be categorized. One is digital frame camera, another one is push broom, and there are 3 categories of wish broom scanning mirrors. Wish brooms scanners with scanning mirror and single discrete detector. This wish broom scanning mirror with multiple discrete detectors, and wish broom with scanning mirror and discrete detectors, and also hyperspectral area array. So there are 6, as I told you. One is digital frame camera, another one is push broom, and there are 3 categories of wish broom scanners, which is wish broom scanners with scanning mirror. Scanning mirror is common for both, and one is scanning mirror and single discrete detectors. And discrete detectors here we skip filters. So single discrete detectors, one is with scanning mirror and multiple discrete detectors, and the other one is wish broom scanner with scanning mirror and discrete detectors or dispersing element. And the other one, 6th one, is hyperspectral image area array. So when it comes to digital frame camera, there are certain advantages of that. One is well defined geometry and also low integration time. And when it comes to disadvantages, as usually many detectors require. So one then comes to push broom sensor types. They have a uniform detector response to long track direction, and also no mechanical scanner and somewhat long integration time. So those are advantages. So goes a long track direction, and also no mechanical sensors, mechanical scanners, and also somewhat long integration time. That's one of the key advantages of push broom scanners. So disadvantages are many detectors are required per line, and also complex optic system is complicated in here. And when it comes to wish broom scanning mirror, wish broom scanners with scanning mirror and single discrete detectors, and also the advantages of this type is detector response over the scene, of course, and also simple optics when comparing to push broom. And also when comes to disadvantages, the short dwell time per pixel is one, and also high bandwidth and time response of the detector is another. These are the key disadvantages when it comes to multiple discrete detectors, and also wishbone scanners with discrete detectors as well. Disadvantages are same. And also when comes to advantages of multiple discrete detectors, one is of course simple optics is common for both multiple discrete detectors and multiple discrete detectors, but when it comes to multiple discrete detectors, they uniformly detect response to over the swath, but scanning discrete detectors response over the scene of swath. So here a single discrete detector response to over the line, multiple discrete detector response over the scene, over the swath, and the other one is so push linear array detector response along the track direction. So which when single discrete detectors response over the scene, and multiple discrete detectors response over the swath, and also uh, discrete detectors response over the scene of swath. So these are the advantages of each type. So it's easy to remember, same thing with differences. And I told you about when it comes to push broom and hyperspectral area, advantages and disadvantages are same, which are uniform detector response along the track, and no mechanical scanner, and bit long integration time, and additional one is when it comes to hyperspectral area array is more and narrow bands possible. So this when comes to disadvantages of close complexity of optics, and number of larger number of detectors per line requirement is are the disadvantages. So these are when advantages are disadvantages comparison of sensor types. So I think you learned a lot today, comparing platforms, sensors and scanners, as well as the orbital characteristics of remote sending satellites. So it's a big lecture, so I suggest you to revise it again and again. So many additional stuff was explained by me when discussing these satellite which were not included in these satellites, of course, these slides, of course. Satellite system, and also categories of some examples for sensors, and also these explanations about these types of scanners as well, and also advantages, disadvantages, comparison of these scanners, sensors. So of course you learn a lot from this lecture, a bit longer one. So we'll continue this lecture series with the next part, and hope you learn something from this lecture as well, and leave a comment on things you think we need to improve. And we upload these videos frequently these days, and if you want, subscribe our channel and turn on the notification bar, for it makes you easier to stay in alert with our channel when we upload videos on this lecture series. So thank you for joining with us. Have a nice day.